Okay, in this first part of the lesson on stars, the first thing I'd like to talk about is the difference between brightness and luminosity and the numbers that go along with them, which will be apparent magnitude and absolute magnitude. As you saw from the slide that I just displayed, brightness is the word that we use when we're describing how bright do humans perceive a star to be, whereas luminosity is more of an absolute number that means how much light is that thing really putting out. The main thing to keep in mind about the brightness scale is that brightness is measured by humans from Earth, whereas luminosity corrects for how far away the star is from us. So some stars that will appear very bright, for example, our Sun and Polaris and Vega, are only bright because they're close. Other stars are extremely luminous, but because they're so far away from us, they're not all that bright to the human naked eye. The oldest scale used for star brightness comes to us from, some people say from Hipparchus, and some people say from Ptolemy. In either case, Ptolemy certainly popularized the usage of this 1 to 6 scale for star magnitudes measuring their brightness. Nowadays, we call the scale that's used for this sort of thing, for the brightness measured by humans from Earth, we call this the apparent magnitude scale. One thing that's strange and tricky about this scale is that the ancient Greeks who made this catalog basically took all the brightest stars in the sky and called them 1, which means a low number means a bright star. The other strange thing is that when we went back and made measurements of how truly bright these things were, it turned out that the stars that were named a 1 on this scale were about 100 times brighter numerically than things that were given a 5. For this reason, an astronomer named Pogson in the mid-1800s decided to define a magnitude 1 star as being exactly 100 times brighter than a magnitude 5 star. And so that means that there's roughly a factor of 2.5 difference between each one of the numbers in the magnitude scale. A 4 is 2.5 times brighter than a 5, a 2 is 2.5 times brighter than a 3, and so on. And a quick reminder, apparent magnitude M connects back to the brightness of stars as seen from Earth. It uses the lowercase letter m, and it's different from the so-called absolute magnitude, which is connected to an object's luminosity, which you'll see in the next slide. So to recap what you saw on the previous slide, we use lowercase m for brightness, and we use capital M for luminosity. But what all this means is that we've got a scale for magnitude that is a logarithmic scale, meaning that it goes by factors, multiplicative factors, rather than adding and subtracting. Logarithmic scales can be confusing, so I'm going to spend a few minutes here reminding you about some logarithmic scales you might have seen before this class to make the connection. The main thing to know about log scales is that they're sort of suited to the fact that humans are good at distinguishing between things that are really different from each other, but not so good at distinguishing things that are close to each other. If you'd like to see an interesting example of this, then Google UNSW decibel, and you can find a really interesting page on sound loudness. On this page, it plays several sound files to show you that you can tell easily when the difference between two sound loudnesses is big, but you can't tell very easily when the sound difference is not very big. That's why the decibel scale is an example of a logarithmic scale. So sound loudness is a great example of a logarithmic scale because Every 10 decibels represents a difference in a factor of 10 between how loud the sound is. In other words, something that is 50 decibels would be 10 times as loud as something that's 40 decibels, and something that is 30 decibels would be 100 times as loud as something that's 10 decibels. Normal human conversation is about 60 decibels in sound loudness. A hair dryer or a lawnmower, when you're really close to them, are about 90 decibels, and that's close to the range of human hearing loss as you get exposed to these for a long time. Construction equipment, jackhammers and drills and things like this are in the 130, 140, 150 decibel range, and they're extremely dangerous to the human ear. 190 decibels would be enough to basically kill your ears. On the other hand, the reference point for the decibel scale is basically the quietest thing that the average human can hear. That's what we define to be 0 decibels. And that is a thing that you'll find in common with all of these different log scales, is that they all need a reference point. And usually this reference point has to do with humans or what humans use to measure things. Earthquakes are another good example. They range from 1 to 9, which is a pretty small scale, but each number represents a factor of 10 difference in the strength of the earthquake. So a 2 is 10 times as powerful as a 1, and a 4 is 10 times as powerful as a 3, and an 8 is 10 times as powerful as a 7, and so on. A magnitude 2 earthquake, humans wouldn't even really feel it. Your dogs would definitely feel it, and they would go crazy, but humans generally wouldn't. A magnitude 4 earthquake you could probably feel, but it would just be kind of a slight shaking, a slight tremor, a slight sense that something's not right. On the other hand, a magnitude 8 would take your house down. Another good example is the octave scale for music. Musical notes, in general, you could say they go from the lowest note on a piano, which is called A0, to the highest note on a piano that's called C8. Here the scale factor is 2, meaning that an A1 has twice the frequency of an A0, and an A3 has twice the frequency of an A2, and so on. Each note that goes up 1 octave is twice the frequency of the note before. The reference point for this is the lowest C note on a piano, and I suspect this is because the guy who came up with this whole scale, his name was Bach. He wrote most of his music initially for piano and did all this stuff on a piano as he played it and tuned it. A couple of examples. Most American orchestras tune their instruments so that A4 is a 440 hertz note, so most musicians know the A4. And one of my favorite songs by Jimi Hendrix, called Hear My Train A-Comin', in the best guitar solo, he hits a high D8, which is crazy. One that you might have learned about in chemistry or IPC is the pH scale for acids and bases. That again is a fairly small scale number-wise. It only goes from 0 to 14, but each difference in number represents a factor of 10 in how strong the acid is. So for example, a pH of 4 would be 10 times as acidic as something that has a pH of 5. Water is the reference point in this scale. Water is defined to have a pH of 7. It's exactly halfway between being an acid and a base. It's neutral. A couple of examples. Lemon juice and vinegar have a pH of about 2, whereas battery acid has a pH of about 0. It's extremely caustic. On the other end of the scale, milk has a pH of about 7. Hereford's drinking water has a pH of about 7.6. Baking soda has a pH of about 10, and drain cleaner has a pH of about 14. Another example that I don't know very much about, but I've learned some from Mr. Grace and Mr. Tillman, is the use of f-stops in cameras for photography and for filmmaking. Essentially, these are those weird numbers that you can control by turning the knob on the camera lens. From what I've read, practically speaking, they go from roughly f1.4 to f22, though I think a lot of specialized cameras can go lower than that and higher than that. In any case, there is a scale factor here. Each f-stop is about a factor of square root of 2 different from the next. I'm not really sure what the reference point here is. I'm sure that people who understand photography better than I do would be able to tell you. An interesting example that I read about was a guy who was talking about trying to take pictures of a bear trying to catch salmon inside of a river. In the picture you just saw, he was trying to capture the action and freeze the instant, so he used an f2.8. In the second photo, he wanted to kind of show the action taking place over a period of time, so he introduced some blur into the picture and used an f22 instead. And this brings us to the whole reason I was teaching you about log scales, which is the apparent magnitude scale, lowercase m. This scale goes from about -27, which is where the sun is, to about +30, which is the dimmest star that can be detected by our best telescope, the Hubble Space Telescope. I'll point out again that there's some weirdness here. A -27 means extremely bright, a low magnitude means a bright star, whereas +30 means a very, very dim star. In Pogson's system, Polaris was defined to have a magnitude of exactly 2, and that was the reference point for the apparent magnitude system in the 1800s. Near the end of the 20th century, we redefined the magnitude scale a little bit and set Vega to have a magnitude of 0. So our common modern standard is that Vega is defined to have a magnitude of exactly 0. You'll see lots of examples of these magnitudes, and in fact, I've got a paper for you that I'm going to make available inside Schoology that has a list of a bunch of star magnitudes. But a couple good ones to note: the sun is -26.7. Remembering again that low and negative numbers mean bright, this is a reminder that the sun is extremely bright compared to stars. Similarly, the moon, when it's at its dimmest, the new moon, is about a -2.5, whereas a full moon is a -13 when it's as close as it can get. Polaris in our modern system has a magnitude of 1.98, and Sirius, which is the brightest star in the sky other than the sun, has a magnitude of -1.46. Finally, we have the absolute magnitude scale, capital M. It's got a lot of similarities to the apparent magnitude scale, lowercase m. The range goes from roughly -10 for the brightest blue stars to about +17 for red and brown dwarfs. Just like with apparent magnitude, a negative number means a very, very luminous object, and a positive number means a very, very dim object, not very luminous. It goes by the same scale factor, 2.5 times. The reference point is a little bit tricky to talk about, and I don't think you would really benefit much from learning here, so you can read about it on your own if you like. But it has to do with intrinsically how much light something puts out when it's a certain temperature. The sun has an absolute magnitude of +4.83, which I think is an interesting thing to compare to its apparent magnitude. One way to put it is that the reason the sun is such a high apparent magnitude is because it's really, really close to us. It's not intrinsically all that bright a star. It's a yellow-white dwarf, and so it's not really all that luminous as far as stars go. So this is a good way to show the distance correction, that the sun is not intrinsically all that luminous, but because of its distance being so close to us, it's very, very bright. Notice that the moon doesn't have an absolute magnitude, and that's because the moon is not a luminous object. It's not producing light on its own. It's only reflecting light. The last two examples that I've written here I think are kind of interesting, because Polaris has a magnitude of 2, meaning that it's not a terribly bright star. However, its absolute magnitude is -3.6, which means it's very luminous. In other words, if Polaris were closer to us, it'd be a lot brighter in the sky. Sirius, which is the brightest star in the sky other than the sun, has a apparent magnitude of -1.46. But in terms of its luminosity, it's not really that luminous compared to Polaris. It's a 1.4 on the absolute magnitude scale. To put it another way, Sirius is only bright because it's close to us. If Polaris were as close to the Earth as Sirius is, then Polaris would be bright enough to cast a shadow at night.